I'm from WSO2. So today's talk is going to be on performance. So my background is I also have a software engineering background. So I've worked as a software engineer and then technical lead and software architect, and also I've done research in the performance area. But at WSO2, what I'm focusing on now mainly is performance. So the key areas. So I will first introduce, just give a general introduction to performance and why it is important and so on. And then I will talk about three main areas in the performance. So basically, performance testing, performance analysis, and performance modeling. So basically, I want you to get like an overall understanding of these three main areas. So why performance? Now, so here what we are talking about is the product performance, right? So performance is very critical, like so, especially for certain customers when they do the vendor evaluation. What they do is they look at the performance of different products, similar products from different vendors, right? So they do performance evaluations. So based on those evaluation results, right, they decide which product to buy. So we have had many cases like that, but it is only for certain customers who are very critical about the performance, right? So now one thing that we have to remember is that when the customers when do such performance evaluations before they purchase, they actually do it for very specific scenario, right? So I mean your product may have different configurations, different deployment patterns, and so on, right? So basically you have to kind of make sure that for that particular scenario, and also there's a performance metric, like we talked about latency and so on. There are other performance metrics like throughput, utilization, even people measure things like load average. So, so when they do such evaluations, they don't look at the performance under all of these ones. They just look at it for one performance metrics, for example, throughput. And then they do make that decision. Now, performance is an exciting area. It is also very challenging, right? So why is it challenging? Now, that's because the systems are these days very complex. So you have it's not just single server which you're talking about. You have one server talking to another service, and then you have these different patterns, right? So it's very difficult to understand the performance of such systems, right? So, and for example, if there's one bottleneck which you think might be causing an issue in your system, you fix it, but actually then you realize it's not fully solved because there's another bottleneck. So that is one of the characteristics of the performance. Now the other thing is that performance is now generally in the technology disciplines, things are objective, right? So if you have a bug, you fix the bug and then it is fixed or it's not fixed. So it passes all the test cases. But with the performance, it can be quite subjective as well. Like, for example, for one person, that the performance of your product, okay, it can process this many requests per second. That may be enough. But for another person or another party, that is not enough. So we have this kind of characteristics. Now, there are many areas in the performance. So performance testing is, I'll be talking about only three areas. So we have performance testing. So testing is the process that you actually carry out to get the performance results. So once you have the results, you have to analyze it, right? Then comes the performance analysis. Now, once you analyze the performance, of course, if there are issues, so if it is not performing well, if your product is not performing well, say for example, latency is too high. You want your latency to be less than 30 milliseconds, but you realize that it is 50. Right? So then you have to basically optimize it. So, and that is performance optimization. And then attached to that, you have performance tuning, right? Now, so these are like different areas. Then, of course, there is performance modeling. Now, I'll talk about this in little bit more detail later. Also, there is performance troubleshooting. Now, this is a very difficult area. When you have a bug or performance related issue in your system, finding out the root causes can be extremely difficult. Now, there are methodologies for doing it, but today, because of the time limitations and all that, I won't be touching that area. Maybe we can have a talk on that at some later point. So, okay, now let's have a look at performance testing. So, basically the basic idea is that you want to understand how your system behaves, right, under different workloads. So, you change the workload and then you see how it behaves, right. So, normally the performance testing process would have to be completely automated. Right? So, automated means you run the test and tomorrow morning you come, you have the results. So, there is no manual intervention. So, for example, once you finished one test scenario, you might have to restart the servers and run the next test. So, basically part of the automation is even sometimes things like you have to restart servers or clearing up databases and so on. So, all that would have to be automated, otherwise it can cause a lot of problems. So, after you've done the performance test, what you have is results, right. So, so what are the core things? Now, this is like a block diagram, like you have a system under test, you have some input workload. Now, I'll talk about this, and then you have the resulting performance. So, this can be a web server or some 3-tier architecture system, or can be a middleware system and so on. Now, when you deal with certain specific customers, they might have certain requirements, right. So, and of course, if it's not satisfied, then you have to, improve the performance, and there are ways to do it. But in the product releases, what we usually do is you compare with the previous releases performance results. So, you have your previous releases performance results and you test it now, and then you check whether there's a significant or whether there's a degradation in the performance of your product, right. And if there's a degradation, then of course you have to go and fix it. Otherwise, it's actually good. You get an improvement. Now, the other thing is identifying the performance testing environment. Now, this is an also important aspect. So, we have to decide where you are actually going to run the tests on, hardware, network, is there going to be any virtualization, are you running it on EC2, right. All of these factors will have an impact on the results. Now, the repeatability of performance tests is also important. Now, we have had situations where you run the test in the morning, you get some results, and in the afternoon you run it, you get different results. Now, and that is because of reasons like we are actually using shared systems. Like while you're running it, some other guy came and ran different tests, and it had an impact on the performance. So, these things we have to be extremely careful, right. So, you have to define test cases. Now, for a given system, you might have different use cases, right. So, for example, if you take a web server, you might have a search operation, or you go and have you can go and fill a form, right. So, these ones actually can be different use cases, or maybe a combination of these things, right. So, that is what you have to define. And then the workload. So, how do you actually put the work? How do you actually load the system? So, you have an external thing which you call the performance testing client, and then you have your system. So, this is the guy which generates the workload and send it to this, right. So, what you usually do is you simulate, or you have you call this concurrent users. So, you have multiple clients, right, sending request to the system that you want to test. So here we have like a sample here, like this one shows. Now here we have in the x-axis, you have a concurrent users. So as you increase the concurrent users, now this axis is, I'll talk about this performance metrics later on. This is the throughput. Throughput is the rate at which your system is processing requests. So once you increase it, the throughput improves. Right. So now also you have to consider different deployment patterns, right? So your product may have like a all-in-one deployment where you deploy it just on single server, right? Or if it has different profiles, for example, you might want to run one profile, say one JVM for each profile. So you run one profile on one server and another profile on another server and so on. So, and that is like a distributed kind of deployment. So this is another thing that you have to take into consideration when you do performance testing, right? Which deployment patterns that we are going to test, right? And of course, there are other things like databases. Now, this is recent performance results which we did. We have a product called WSO2. We have a product called WSO2 stream processor. What it does is, so basically you have a stream of event coming, and then you can do different operations on it. Now here we actually persist each event using a database. So it's not in-memory processing. You go and persist the event or that event which you receive into a database. So what we noticed was, when we are using MySQL as a database, once the database size exceeds a certain limit, you get a degradation in the performance, like this. Right? So this is the throughput, again, number of messages processed, right? But when we use the MS SQL or Microsoft SQL, or maybe you can use Oracle or something which might have similar behavior to that, there is no such degradation. So in this case, basically you have to purge, or maybe we have to use some cleaning to get the performance up. So now sometimes also there is an impact on the request size. So your system receives a message. So depending on the size of that message, the performance could vary, right? So if you have if you want to do some processing, say for example you have a JSON message and you want to transform that one to an XML, right? So the processing depends on the actual size of the message, right? So therefore sometimes you have to also the network latency. So if it's a large request, the transfer time will be higher. So you have to even test it for different message sizes. So here you see that as the message, so this is for, this one is, so again this is the throughput. This one is for a larger message size where you have the lowest performance. Now also there is this thing called think time. Now when we usually do performance test, what we do is you send a request to the server, like in a normal client server architecture, you get the reply. Immediately after that you send it. Right. That's like a stress test type of thing. But sometimes if you want to do more realistic tests, you have to have time between these requests. You call that think time. So you can actually vary the think time. So what happens is when you increase the time between requests, you actually reduce the workload going into the server when you increase it, because you have less number of requests going. So that's another thing which we can control, right? Now, then again, there is other things like when you define the test case, there are things like back-end services, right? So you might have some middleware. Say for example, here we have the API management solution here. So here, which receives traffic, and this one is connecting to a back-end service, right? So, which is an external thing. But actual performance depends on what the latency of that back-end service is, right? So some weather service or something. But we actually cannot use that actual service, so we have to somehow mock that. And then you mock it and then what you do is you vary that backend service latency, and then you can do different tests using that. For example, there can be certain backends. Now, backend here is I'm talking about a backend service. Now, that service might have a database, that is fine, but some backend services may be quite fast, right? But if you might have a case where there is some big computation happening, then it will affect the total latency, right? So what we do in that case is we kind of try to mock it and then change those backend latencies. You write a small program. When the request comes, it will purposely delay it and then send the reply back. So so that is about basically coming up with a performance test plan and things that you can change, and then what would actually affect the performance. Now, the next thing is identifying the statistics to collect. Right? Of course, we have to collect enough information to derive our performance matrix, right? So throughput. If it's throughput, we need to know how many requests have been processed and the time. Using that, you can calculate, right? Also, you can collect things like load average, CPU utilization, network utilization, GC logs, and so forth. Now, one thing to make sure here is that when you collect such information, you have to make sure that there is no overhead, or at least minimal overhead. Because when you have a system running, when you try to monitor, the monitoring itself can have an impact on the performance, right? So, for example, if you do like extensive profiling, basically that will bring the performance down. So only certain things are allowed. So you can't, you have to monitor it such that, or you have to collect the information such that there is minimal or basically no overhead on the system, right? Now, okay, then it comes to the performance testing tool. Now, there are many testing tools. Now, testing tool is the one that you actually use to generate the traffic. Right? You have your system and there's a testing tool. There are many of those. So there's JMeter, WRK, GetLink, Load Runner, and so on. So basically, the companies will have their preferences based on the features. Now, some performance testing tool can be might not even have a UI. You just run it in the terminal, like this WRK is something like that. You don't care about nice graphical UIs. You just want to do a test and see the results, right? But one thing that we did notice was, now this is not okay, because what we did notice was we tested using different tools. Now, we noticed that we are getting different results for certain cases, which is a bad thing, actually. So ideally, you have 3 different performance load generators, and then you test the same scenario. You should get the same performance numbers, the throughput, latency, and so on. But one observation was that there can be situations where you will get certain differences when you use different tools. But most of the time, the results are very similar. So we actually were thinking like as to why this happens. Now, one reason for this is now the architecture of the testing tool itself. Now, if you take JMeter, for example, in the JMeter, when you do a performance test, a user is a one thread, right? So there is a one-to-one mapping. But with WRK, what happens is one thread manages multiple users, multiple clients. So because of these differences in the internal architecture of the performance testing tool, there's a possibility that you get some variation in the results for certain cases. Now, important thing is that when you want to do the performance test under very high loads. Say, for example, you want to simulate 10,000 concurrent users accessing a given system, right? So, and for that, just using one instance of the performance testing tool is not enough, because it cannot actually generate enough load. So what you do in such cases, you have to cluster it. Like you have, so this is a JMeter, which is a tool for performance testing tool. So this guy generates traffic and send it to this, and then it gets the reply back, and then and so on. And there's another instance of the performance testing tool, right? And there's a coordinator. So basically, we have two generating traffic and sending, and this guy, which is we call the client, is the one that does the data collection and so on. So if you actually if you don't cluster, you might actually not get the proper performance. Like for in this case, like we have a case where, so this is a case where 2,000 concurrent users accessing a simple netty server, right? So what we notice is, if you have just one JMeter instance, although we specify the concurrency as being 2,000, the TPS, number of request process, is 42,000. Here we have increased it to 2, you see an improvement. So that is another aspect, but this only applies to very large workloads, right? Now, one final thing, of course, you have to do is, before you do the things, you have to figure out also the tuning, right? So there might be some OS level tuning, if your program is Java JVM level tuning, and so on. And also there is application level tuning also. You might have a thread pool. Now what is the optimal size for this? All of those things would have to be considered, and there might be a case where you have to, these parameters themselves are not fixed, right? But usually we try to keep them constant, right? So you have, say, 100 different test cases which you have defined. You don't change these ones, but maybe except for the JVM heap memory, which you sometimes change depending on the client requirement. So that is actually going to create another set of tests. So basically you test your system with low memory. Say for example, you allocate maximum 2 gigabytes, and then you get the results, and then you test it again using 4 gigabytes, right? Because certain customers, they would say, I don't want to have more than 2 gigabytes of memory, right? So we want to know what the performance is. The last thing is basically running the tests itself. Now, okay, so that is all about performance testing, like what we have to do, what are the tools, the factors that we have to consider, the things that you control, like message sizes, deployment patterns, think time, and so on. So once you've done the performance test, what you end up with is data, right? So you get a lot of data. So analyzing this data gives insight into numerous behaviors, like how does the average latency vary with the increasing load? How does the throughput vary with the increasing load? What is the impact on the message size on the performance? And so on, right? What is the maximum latency? Things like that. Or things like how well the system scale, and so on. So now the analysis of the performance, the first thing you have to do is you have to figure out what are the metrics you are going to use, right, to see if it performs well. Now even I think in the first talk we talked about this, the latency. Now latency is a key metric now, and it is becoming more important now. Now there was a time the throughput was important. Now I think we are going more towards kind of the latency, right? So there are cases where there's trade-offs between these ones. Now you try to improve the throughput, but the latency might degrade, right? So so it's simply a measure of weighting. So the definition of the latency itself could be different, right, depending on the system. Like if you take, for example, a simple database query, what is the latency of a database query? So that would be just the execution time, like whatever the CPU time, plus the I/O, like that is the time, the disk access time. So because database is a physical, it's in the physical hard disk, right? So the database latency is the total is going to be the sum of those two, right? So the latency of, say for example, if you take a web request can be the total round trip time. Another term for this, sometimes people use the response time, right? So basically it's the time that you, difference between time that the response is received and the request has started, right? So that is the round trip time, which is the latency. Now if you look at, so this is, so in the JMeter, once you run a performance test, you can create this file called JTL file. Now in the JTL, you can actually see it records the latencies. So here we have 11 records. So these are the latencies for those 11 records. So you have 36 milliseconds, 35, and so on. Right, I have to speed up. Now you can do a simple time series plot, right? So x-axis is the time in this plot. So this is from one of our products. Y-axis is simply the latency. So this can basically, you can get an idea of how the latency varies with time. Now remember, this is a time series plot. Now if you have a spike or something, it might appear somewhere there, but in this particular case there is no big spikes, right? Now, so you have the latency which you define it for a single request. Now then you have the average latency. So the average latency is simply you take the sum of those latencies and divide it by the number of requests, right? I mean number of requests sent during that period. Now these days average latency is not enough. People look at things like latency percentiles. Now, so the latency percent, like for example 90th percentile, 95th percentile and 99th percentile. So what is the latency percentile? Now 50th percentile is of course just for the purpose of explaining, it's the median. But in the performance world we don't look at the 50th percentile, but it is the median. So basically you arrange them, your latencies in the ascending order, and then you get the median, right? So basically what it means is that 50% of your request will have latency less than that value, right? So 23 in that case. So if you look at the 90th percentile latency, so latency again the unit is milliseconds. That means 90% of your requests will have less than that value, right? So basically, like it is difficult to now if you look at the average latency, you can achieve a good average latency, but achieving good 90th percentile latency is difficult. So your system have to design it very carefully to achieve such latencies, right? Because you're basically saying most of your requests, like 90% of your requests will have less than that latency, right? So how does, now this is a plot of, so this axis is actually average latency, right? So this is for a simple performance test. Let's say that this is for you're testing a web server or something, or you're testing some middleware system like the API manager thing which I showed you before. Now this is the round trip time or the average latency. So this is how it varies. So as you increase the concurrency, now remember the concurrency represents the load. You increase the number of users on the client side, that will increase the load on the server. The latency of course will increases. So initially it is linear, but after you increase the load beyond certain value, then it becomes non-linear, right? So this is a general behavior that we always notice. Now this is basically this is a result from an actual performance test. Now you can kind of see it's following the same patterns, right? So here we have the average latency, and then we increase the number of concurrent users. By doing that, we increase the load. Now there's a linear behavior here, but when it gets to 2,000 concurrent users, 2,000 clients are sending requests, it becomes like almost that part, the growth is not 100% linear. Okay, so we talked about latency of individual requests, we talked about average latency, and then we talked about latency percentiles. Now we get to the latency distribution. Right? So the latency distribution is everything. You can derive all of those statistics using this. Right? So basically now, so it is a probabilistic representation of, now this axis is basically the latency, of course, right? And this axis is, this should be the probability type of thing, right? So this is like how the latencies are distributed, right? So this distribution can have different forms, right? So in this case, I'm just showing a normal distribution. Now, the most simplest type of latency probability distribution is the histogram, right? Now, latency, of course, is a continuous variable. So therefore, we don't actually have to have a histogram. You can actually fit a distribution into it, a continuous distribution. But if that is too difficult, you can just do a histogram. So basically, you get all your latencies, like the minimum and maximum, and then you put it into bins, right? And then you count 0 to 5, how many latencies are there, from 5 to 10 milliseconds, and so on. So that gives you like a very overall good picture of how the latencies behave, right? So how does the actual latency distribution, look like? So the actual latency distribution is actually most of the time not symmetrical. Even if you run the same workload on the server. Now that is a very interesting observation. So you would expect, like, if you run, for example, if you write a small Java program, right, and then count up to 1 to 100, you run it multiple times, and then of course you will get different times, execution times. And then you look at the distribution of those execution times, you would expect, like, okay, the average is 50, and then you would expect nicely going like this. But that is not what you actually get. What you get is something like this. And this we have noticed in pretty much all of our products. So you get like, we call this right skewed distribution, right? And it's not symmetrical. Now, if you perform different tasks on the server, then it is okay to have, like, for example, if you have a mixed workload, so one time you are like going back to the Java program, one time you are counting from 1 to 1000, the other time you are counting from 1 to 100. Now this, of course, should have non-symmetrical distribution. Now I'm not talking about that scenario. What I'm talking about is the server basically doing the same thing over and over again, and then we look at the latencies, right? So what kind of latency that we get, that is also skewed. So then you ask the question, why does this happen? Why do you get such a skewed distribution, right? Then one of the reasons is that, I think there was a person who talked about cache. You could have things like cache evictions, right? So yeah, there's a database and there's a cache. So every 15 minutes you do a cache eviction. You completely, or basically your thing is not found in the cache, then it has to go to the DB, right? So what happens is that for that particular request, for most of the requests, fine, it is found in the cache, so it's returned fast. But for that particular request which is not found in the cache, you have to go to the DB and get it. Okay, here we go, you get kind of a spike, right? And then there are other things like, now with if you're using Java, there is garbage collection which happens, and in the garbage collection there is a thing called now when you do major garbage collection, it basically there's this concept called stop the world. You completely stop, right? So basically that means for all of the requests which are currently being processed, that time gets added. So basically you have to, once you finish the garbage collection, then only you start processing it. So these kind of things actually add to the latency, and then it's making the latency distribution skewed. And also the network congestion might result in things like this. Now this is, now previously I showed you the histogram. Now this is the continuous distribution. Similar to the histogram, you can actually load your data into something like R or Minitab, or you can actually plot the distribution. Now here, what I'm doing here is I am plotting the latency distributions for under different loads. Right? You can see it's still right skewed, but depending on how much load you applied, the skewness actually changes. Right? So what happens is when you have more load, you have relatively high latencies, right? And that is resulting in so that makes it less skewed with high workloads, right? So those are the things that you can actually look at when you do the analysis. Okay, so now we talked about individual latency, like latency of a single request. Then we talked about average latency and then latency percentiles. Then we had to look at the entire latency distribution. All right. So that is one performance metric. The other performance metric is the throughput. Of course, there is other things like utilization and so on. So throughput is basically the rate at which your system can process things. Right. So the unit may be transactions per second, or messages per second, or requests per second, and so on. So for the throughput, the behavior is like this. As you increase the workload, that is by again adding more concurrent users, you get a linear increase. And then what happens is it kind of stagnate for a while. So you increase the load, the TPS or the rate doesn't increase anymore. It should, but because of some bottleneck or some contention issue, so it increases and then it stabilizes and then it comes down. Right? Basically, by the time it gets to this area, you call this this area is kind of like, you call it steady state, right? And this area basically you have gone out of the steady state, like the utilization is gone above 100%. So then you get a degradation in the performance. That's where you have to either optimize the performance or maybe scale or do things. Right? Now again, this is an actual performance result. Now you see how the throughput increases. Right? So because when you increase the number of users, which is the x-axis, you have more traffic going into your system, right? Then the system has to process. So which, of course, the system has to process more requests as you increase this. But then up to certain limit, it almost becomes constant. But we haven't tested it beyond this point, so you cannot actually see it going down. So that is like a stress test kind of thing, but this is kind of a performance test. If you do a stress test, then you go beyond that point, right? So, so I have to go fast now. Okay, so now we kind of know how to look at the performance. So there are other performance metrics like utilization and so on. So once you analyze it, then you know whether it's performing good or bad, right? Is this performance good enough? We are processing 5,000 requests per second when you have 1,000 users connected to it. So if it is not good enough, then you have to go and do things to improve the performance, right? So that is the now I have only one slide on this because this is a very lengthy topic. So basically there are multiple layers to look at when you want to optimize the performance. Now you have the hardware. You can do hardware upgrade if you want, like use 8 cores instead of 4 cores. And then you might have some virtualization. You might be able to do things there. And then you have the operating system on top of that. You might be able to do some OS level tuning, but generally the OS level tuning doesn't give you a lot of improvements. Then you have the JVM on top of that. Now then you can do JVM tuning, you can do GC tuning if there's a memory issue, or you can do JIT compilation tuning to address certain other issues. The last level where you can get the best, the maximum improvement is actually the change in the code itself, most of the time, right? So that is, I mean, the application level, I mean the code that you write. I mean, you might want to optimize a DB query, for example, right? Or maybe like add indexes. Sometimes, like most of the time, you get performance issues because there are no indexes in the database, or missing indexes or something, right? Or there might be an algorithm which we had to some encryption algorithm or something which is written very poorly. So it doesn't matter what you do here, you cannot get your performance up unless you fix this. So that is the thing that you have to kind of keep in mind. But the levels above can give you certain improvements, but the best performance improvement is basically you get it by the other example is like contentions. Like you might have let's say 100 threads trying to access using a synchronized method or something, right? And then that becomes a bottleneck. There's some kind of a shared resource. So, but those sort of things immediately when you profile, you can figure it out. So when you have such bottlenecks, either you have to take it out completely, or you can kind of like reduce the scope of it. So if you're locking this much of code, basically you can reduce the scope of it. You just lock only the limited section, right? So that is performance optimization. Now let's now go to this one. Now this is performance modeling. Now basically this is not something that people in the industry actually do. I mean, at least not small organizations. Like large organizations might do, like WSO2, we have a lot of intern projects on this thing. But it's actually very interesting. Now basically what's happening here is, now this is more towards like an academic kind of exercise. So this is, you're going from the testing to the modeling. Like it's, the testing guys normally don't care about the models, right? So this is like the other end of performance. Now, so there's white box approach. Now, white box approach is like you model each and every single component and the interactions between them. So there's one service calling another service and another service. You have to know internally how it's done. Right? Now you can use things like queuing theory. I'll talk about this very briefly. So, and then the black box approach is basically the machine learning and things like that. You assume that it's like a black box, right? So you operate on inputs and outputs, right? So basically what happens is, if you go and have a look at, now this, there won't be enough time to do this. Now this is a very simple case where there's a queue and a worker. Now worker can be a thread or server by itself. So basically something like this can be modeled analytically using queuing theory, right? So you have a queue and worker. So you things come in and then you go and process it, right? So you want to know what is the average waiting time in this queue, or what is the average queue length, right? So now what are the things that actually matter? So one thing which matters is like the arrival pattern. So you have a queue, depends. So the waiting time in the queue is dependent on the arrival pattern, right? How fast the things are arriving. The other thing is service pattern. Service pattern is basically the processing time, right? So there's arrivals and then processing. So if you have long processing, then that means it will take more time, right? So, but the thing is, processing time is not fixed. Processing time, you run it once, like I said earlier, you get one processing time, second time you get. So then you get again a distribution. Now the performance is all about distributions, at least at some higher level. So that's why I said like service time distribution, right? Then the service discipline also matters. You can service first come, first serve, or maybe last come, first serve, or whatever. Or you can do things like processor sharing. Like you can process it up to a certain level or limit. Like in operating systems, you have the quantum, right? And then you preempt it and put it back in the queue, right? So it will go back. And so service discipline also has an impact on that waiting time. So this is the only formula I have in here in this presentation. So basically, this is the equation for the average waiting time in the queue, this one. So I'll quickly explain. It actually depends on three things: average arrival rate, which is the service pattern, the arrival pattern, and these two are related to the processing time. These two. Right. So this one is actually the mean processing time. This one you call the second moment of the service time distribution, right? So that is actually kind of a representation of how variable the traffic is. So the more variable the requests are. So for example, let's say there's a request which takes 100 milliseconds, and then you have 1 millisecond request, 1 millisecond requests behind it. Like in a supermarket, one person's got 50 items, and then there is behind that we have 10 people only got one item. So basically what happens is that one big one is going to affect. So that is variability, right? So it's inversely proportional to the waiting time. So basically using such equations, you can model how the average waiting time or average queue length varies under different conditions. Now, because of the time limitation, I'll go to the other one. So there's analytical modeling where you can use queuing theory to get the results, or you go and do the black box approach, which is machine learning, right? So how is machine learning is going to work? Now, when you do a performance test, this is what you kind of get. So you operate on inputs and outputs. You don't care what happens in the middle. So basically these are things you can control. Like this is what I talked about before: message size, sleep time, concurrent users. This is the average latency. So what we are trying to do is, you want to get the performance for a scenario which you didn't test, right? So this is your performance test spreadsheet. You want to get the performance numbers because you can't afford to test everything. Come on, like you have millions of things. So we have actually done this and it has worked quite well. So you train the model using machine learning, build the model, and then using that model. Now in this particular case, we have used this support vector regression. I'm not going to talk about machine learning in detail, but we have identified the features, backend latencies, scenario, concurrency, and so on. And then we have predicted the latency with a very good accuracy. So now you can see the blue one. Now so basically you have that spreadsheet, you divide it into two separate parts, right? In machine learning, that's how it works. You have the test data, and then you have the training data, right? So you use training data to train the model, and test data to test it, right? So if I had like say 200 lines, I will use part of that for training, the other part for testing, right? So this is the test data. So you can see like. So you compare the actual latency, which is the blue one, and then you have the red one, which is the predicted one. Of course, this x-axis doesn't matter. It's for some scenario. It can be message size 100, backend latency this, and so on. So, but it's a very interesting result how you can use machine learning to actually predict the performance. Right. So basically that I think is it. Yeah. So like as I mentioned earlier, the performance is important, not something that we can avoid. Certain customers, it can be very critical. For certain other customers, the features may be important more than the performance. So there are cases like that. So I basically kind of gave like a broad overview of different areas. Performance testing, analysis, and then basically I talked about performance optimization very briefly, and then modeling, which is kind of more towards an academic exercise. So didn't cover troubleshooting, which is another area that people work on. Like you can use things like mind maps for troubleshooting. Like you notice this and then you go and do this and then you do and do that. I guess that's the end of my presentation. Thank you very much.